We are thrilled to have Christopher Blake, Ethan Wrighto, and Max Weeder here today to present Safely Navigating Innovative Successful Cooling Strategies in Plastic Injection Molding. This webinar is sponsored by Maya HPT Simform. Christopher has worked at Maya HPT for 16 years, first as Manager of Engineering Services, then as a Senior Solutions Architect. Now, as Director of New Product Development, he explores new technologies such as cloud computing, simulation-driven design, artificial intelligence, and machine learning, and evaluating technological readiness, go-to-market strategy, and industry applicability. Chris holds a bachelor's degree in systems design engineering from the University of Waterloo and a master's degree in mechanical engineering from McGill University. Ethan is the Director of Marketing at Mantle, bringing extensive experience in technical marketing for design and manufacturing products. Before Mantle, he led the technical marketing team at Desktop Metal, focusing on production-scale 3D printing. Earlier in his career, Ethan worked on rapid prototyping at MIT Lincoln Laboratory, contributing to NASA's Orion mission. He holds a Master of Engineering degree from Boston University and a mechanical engineering degree from the University of Colorado, Boulder. Max is plant manager at CITO and represents the third generation in the company's legacy. His journey began at a young age on the shop floor, where he gained hands-on experience in every aspect of the operation, from sweeping floors and working in production to becoming a toolmaker and later toolroom manager. Today, Max oversees daily operations, bringing deep first-hand knowledge of CITO's products and a strong expertise in PulseCooling technology. Let's give a big welcome to Christopher Blake, Ethan Wrighto, and Max Weeder.
Thanks. Good morning, everyone. Thanks for that really kind introduction. My name is Chris Blake. I work for my HCT, and I'm really pleased to have my colleagues from Mantle and CITO here today to share with you an interesting use case that we've been working on that showcases some of the innovative cooling strategies that are coming out of our respective companies. So in terms of an agenda for this webinar, I'm going to start by just going through some basics, start by introducing the importance of cooling in plastic injection molds, and go through some of the challenges and opportunities that are being faced by members of this industry. Then I'm going to move on and describe the project that we're working on, and then we'll go through and show how our respective technologies work in the context of this project, and show how they also address some of the challenges that I previously identified. Then we'll go through some preliminary results comparing our simulations with experimental data and kind of tee up the next steps that we have planned for this project moving forward that we hope to present either in a white paper or in another webinar later this year. So I think this is old news for a lot of you attending the webinar today, but the cooling phase of the injection molding process is important because it consumes, up to 80% of the overall cycle time. And so optimizing cooling has a very direct impact, not only on the quality of the parts that you're producing, but also on the efficiency of your production throughput. Furthermore, we all know that uneven or insufficient cooling can lead to important part defects like warping and sink marks. So insufficient cooling or even excessive cooling can cause other issues as well, like differential shrinkage and improper shaping of the parts. And if this is not addressed early on, it can result in much longer mold trials. Sometimes, a short cycle time is planned during the quoting phase or when bidding on a specific project. And, we hope that we're going to meet that, but design proceeds as it usually does. Ultimately, there are limits to what the technicians and the tooling engineers can actually do on the shop floor to achieve those cycle time goals. So that's why having an upfront understanding of how efficient your cooling process is actually going to be will help later on down the line. On top of those challenges with respect to cooling of injection molds, there are industry challenges that are being faced by molders and mold makers alike. So in order to stay competitive, especially with offshore suppliers, lead times for the design and manufacturing of parts are becoming shorter and shorter. And there's also a shortage of skilled labor in the industry, which is becoming more and more important, putting pressure on the existing molders and mold makers. So easy to use yet insightful simulation of the injection molding process, as well as generative algorithms that accelerate the design process, are really going to allow mold designers and tooling engineers to improve and accelerate their workflows and avoid lengthy mold trials and costly rework that could happen after discovering issues at those mold trials. Furthermore, there's a growing emphasis on sustainability and reduction of energy consumption. So more intelligent cooling strategies, especially with in-mold sensors and controllers, is going to help save energy by cooling only when necessary. Lastly, traditional manufacturing methods involve multiple steps. They can involve multiple machines, especially for complex molds. And those not to mention, they also put limits on the cooling strategies that are available to tooling designers. So automated tool making and 3D printing address many of these limitations. So that segues well into the objectives of this joint project between SimForm, between Mantle, and CITO. So we decided to collaborate together in order to demonstrate the technologies that I was just alluding to on an actual production mold and show how the advantages that they bring in terms of manufacturability, in terms of optimizing cycle time, and also in terms of energy savings. So here's the part that we actually examined within our project. It's a thaw snap lid. It's a relatively simple part that we're looking at, but nevertheless, it does have some interesting features. You'll notice that around the handle on this right-hand side, the areas are much thicker in order to ensure structural integrity. There are some branding details underneath the lid, and the hinges here necessitate a sliding action in the mold. It's about a 30-gram part, and it's manufactured using 30% glass-filled nylon with the thermal properties that you see on the screen here. Here's an image of the actual mold itself, which was initially designed by CITO with conventional machined cooling channels, as you can see called out on the right-hand side. There's a channel in the cavity side and one in the core side. The mold has also been instrumented with cavity side and core side in mold temperature sensors. And you can also see right here the two sliding actions that put pins through the hinge holes of the part. The mold is made out of P20 mold steel. And here's a quick overview of the processing conditions. So the melt temperature or injection temperature is 280 degrees Celsius. The ejection temperature as recommended or identified by CITO was 72 degrees Celsius. The resin manufacturer recommends a target mold temperature of 62 degrees Celsius, but interestingly enough, the water that is flowing through this mold is actually at 4 degrees Celsius. Max will allude to why that is the case later on in the presentation. And we have a water flow rate of 2.1 gallons per minute. The cycle time, combined cycle time for continuous cooling of the mold halves using the conventional channels is, if I add that up correctly, 48 seconds. 35 devoted to the cooling time, and we'll look at how the pulse cooling technology actually lowers that cycle time later on in the presentation. So the question becomes, how do we simulate all this? How do we use simulation to actually help us with the design of the cooling channels and ultimately improve the cycle time? So that's where SimForm by my company, by MyHCT, comes into play. So some quick background on our company. So MyHCT is an engineering solutions company. We've been in business for over 40 years now. Our primary business is in the development of software for designers and engineers. We've developed over 35 software modules, many of which are branded under Siemens Digital Industries software, meaning they're sold under that brand. We're a #1 worldwide partner with Siemens DI, both in terms of being a software development partner for them, but also in terms of a reseller in North America and Europe. Because of this global reach, we have over 7 million users worldwide, which is pretty awesome. Many of our customers are in fact in North America and Europe, and they're engineering firms that are developing innovative products, but also there are a lot of manufacturing companies like those attending the webinar today who are producing not only tools and manufacturing systems, but also these products. So our team's experience covers many different industries, including discrete manufacturing. In particular, we've performed simulation studies of injection molds for several customers, but we went even further and developed some automated tools for these customers to help them gain efficiency in their mold design process. And this allowed us to gain a lot of critical knowledge in the plastic injection molding industry, especially when it comes to mold cooling, that we've leveraged into the development of our product, which is called SimForm, or one of our products called SimForm. So SimForm is mold simulation that everyone can use. It is targeted at all members in the value chain of the plastic injection and compression molding industries. So mold makers use SimForm to help design their tooling to ensure part quality, high part quality with uniform temperatures and minimal hotspots on the tool during the injection molding cycle. Injection compression molders use it to help optimize their production by reducing that cooling cycle time. And OEMs and suppliers use it to help design and create manufacturing ready plastic parts with fewer iterations with the supply chain to get to market much faster. So SimForm is an easy to use and fast simulation tool that can produce results in less than 15 minutes and help you evaluate not only the temperatures on your plastic part as the injection molding cycle progresses, but also temperatures within the mold itself so that you can evaluate the placement of cooling channels, have an idea of the cooling time, and really avoid over designs and redesigns and save money by doing so, and help you to justify the use of more expensive, potentially cooling strategies that are ultimately going to improve your part quality and reduce the production costs. So things like higher conductivity inserts or even conformal cooling. Our differentiators are that we're a cloud-based solution so that we can leverage powerful compute in the cloud. We have a easy-to-use interface that is meant to help get answers for design for manufacturing of tools and parts much faster, and we leverage some generative algorithms to help with the design of cooling channels. So enough about the company. I'll actually jump into the project that we're talking about. So here's the actual setup of the mold within SimForm. And I think to actually show it a little bit better, I'll bring up the software itself just so you can see what it looks like. So here's SimForm in my browser. I have my project defined for this collaboration that we're working on today. I can open up one of my simulation cases, and you can see the 3D CAD of CITO's mold uploaded into our platform. Basically, you upload a CAD file, and you can upload multiple CAD files, which is going to allow you to define your simulation case. I can have multiple simulation cases. You see I have already ran a few of them. On the right-hand side here is how we define the actual problem. So for CITO's mold, we have the stationary mold half here. We have the moving mold half here with the sliding mechanisms and the insert for the branding underneath the part. We have a separate mold group just to identify the sensor locations. And then we have the plastic part identified as nylon 30% glass filled. Even the cold runner is identified as well. And then I can show you the cooling channels that are designed into the base mold design. So we have channel 1 here on the bottom on the cavities, on the core side, and channel 2 on the cavity side. And you'll notice, unlike typical simulation tools, there's no meshing. All you have to do is identify the different mold components, and you can go ahead and submit this simulation. So back to my presentation. So what we did was we did an initial continuous cooling simulation of this mold and of this part. And what you see displayed on the screen is a simulated estimate of the safe ejection time, or what we call the freeze time, for the different areas of the plastic part. So how long it takes locally for the plastic part to solidify and be ready to be ejected out of the mold. And you can see that location 1 of these two, we'll say hotspots, location 1 takes about 32 seconds in order to be ready to eject, where elsewhere it's lower. So this is indicating to us that we could lower the overall cycle time by tackling just this region on the right-hand side. And conveniently, that's where we have an insert designed into the mold. So one of the challenges that we noted at the beginning of this presentation, if you recall, was the loss of expertise and the market pressure to deliver tooling solutions quickly. So this is actually where generative design really helps. So using SimForm, we can actually provide just the 3D CAD of this snap lid and have the software recommend the most important regions where cooling channels need to be located using an optimization routine. And we're working to add other accelerations to this process using AI. So here in the right-hand picture, you see for the snap lid in pink all the regions that were recommended by the algorithm where channels need to be located and to ensure more uniform temperatures on the part at ejection time. If we overlay the recommended regions on top of the insert, we see where the cooling channels need to actually be placed to get that more uniform surface temperature. Now we could drill in inserts like a U-shaped channel or a couple of baffles into this insert, but really the optimal locations are better served using a conformal cooling design as shown here. And on the right-hand side, you can see the channel carved out of the actual insert. So within SimForm, we can actually simulate this new mold concept and do a side-by-side comparison. And I'll just bring that up here. So I can spin around and actually look at a cutting plane through the mold and have a look at the different temperatures through the mold. So you can see that it is actually much cooler now in the location of the of the handle, so that we're getting, better temperatures, and it's no longer the hot spot within the mold. It actually has shifted elsewhere into the mold, as you can see right here. So if we look at the freeze time estimate, for this new design, we see that the overall cooling time has reduced to around 28 seconds, so by about 4.5 seconds. That's a 14% reduction, which means we are actually, have a non-negligible increase in our production throughput. That said, there is an interesting question to pose. So is this insert actually causing the mold to be too cold in this region? Are we wasting energy to actually cool down the water flowing in this extra channel? We'll kind of allude to that and revisit that later on in the presentation. So we have the conformal design, we have a 14% cycle time reduction. Now the question becomes, how do we actually manufacture this insert? For that, I'm going to turn it over to Ethan to talk about Mantle.
Awesome. Thanks for that, Chris, and the introduction. I'm Ethan from Mantle, and I'm going to share a little bit about how do we actually build this thing. We have a great design. We've simulated the results. We have a theoretical 14% improvement, which is awesome. But if we were to go down to our tool maker and show him this design and say, hey, machine this for me, I don't think he'd be too happy with us. So we have to understand to come up with a way of how do we actually build this thing. So that's where Mantle comes in. I'm just going to share a little bit about Mantle and give a brief introduction, and we'll be certainly part of that follow-up report that we're going to put together as well. But the insert here was about 1.5 inches by 1.5 inches by 1 inch, and we were going to print this in H13 tool steel using Mantle's technology. If you're not familiar with Mantle, just a brief introduction. We are a metal 3D printing company. We tend to call ourselves an automated tool making system. But what sets us apart a little bit is that we were explicitly designed for tooling, meaning precision tools like the injection mold tools that we're talking about today. Our technology combines CNC machining, 3D printing, and software to produce these really high quality, precise, smooth precision tool steel inserts. I have some on my desk here today. I have some others that we'll show later when we're talking specifically about CITO, but hopefully that comes across on the camera, but really high quality inserts designed for printing to hopefully allow you to save time, save money, optimize your toolmaker time, which is so valuable these days with the labor challenges, accelerate your product validation, increase capacity, and specifically what we're talking about today, improve cycle times with things like conformal cooling. Our technology is a little bit unique compared to a lot of other 3D printing or metal 3D printing technologies you may have heard of, and it involves a couple of different steps across two main systems, the printer and the furnace. And I'm going to walk you through this here, and I have a brief video to show you because the couple steps involved to get to the beautiful parts that we have here today. But first, I want to start by talking about what are we actually printing. If you're familiar with other metal 3D printing technologies or even a plastic 3D printer like I have here on my desk that uses a filament, we're quite different in that we are actually printing a metal paste. So very similar to that toothpaste that hopefully we all used this morning. It's a paste, it's a slurry. And what that paste actually is a combination of metal powder, some binder similar to a glue, and a solvent. So these are our tool steels, and it's pretty crazy when you look at this paste in person to think you go from a slurry paste, toothpaste-like material to a hard tool steel in just a couple of steps here. But this is what we're starting with here as a metal paste. Inside of our printer, which you can see here in the bottom right, every single layer, we're going to lay down a layer of this paste, a very small layer, about 100 microns thick. We're just extruding the material out of a needle. Since it's viscous enough, we don't have to heat it or anything like that. We dry every single layer to firm it up a little bit. This actually removes the solvent out. So if you can see in my little illustration up top, those yellow bricks are gone because now we've removed the solvent out of the material, firmed it up, and then we machine it. Every single layer, this is happening over and over again to build up the part. Since the material is very soft in this stage, it's just a dried paste, we can machine really quickly. We can also use some really small cutting tools since there's very, very low cutting forces. The smallest tool we're using today is a 6-thou ball and mill, so some really, really small tight features, which is really, really important, of course, for mold tools. After printing is complete, You take this part, which is just now binder and metal powder held together, and you put it into a furnace. If you're familiar with powdered metal or metal injection molding, this is a sintering step. You get just below the melting temperature of the material, and the metal powder actually fuses together. What's a little unique about Mantle is that since we've dried and compacted essentially every single layer, our shrink rate's only about 9%, versus a MIM process or other sintering processes are normally closer to 20%, which allows us to control the tolerances much more accurately than these other processes to get you closer to those final tooling tolerances. And of course, with that excellent surface finish, thanks to the machining step. Just going to show a quick video here to help you understand and put this all together. You can see that metal paste. It just comes in these tubes. You install it on the machine. That's just the build plate here that you put in. You're just depositing that paste out of the needle just to extrude that paste out. We're then going to come through and dry it. That's going to firm it up, remove the solvent out of the material, and then every single layer is going to be machined, either perfectly flat or contour milled with a variety of different cutting tools to refine the shape, to improve the surface finish, and really clean up the design here. So this process repeats over and over again to build up your part. We can do really, really deep ribs, conformal cooling, all of these things that would be really, really challenging with traditional manufacturing because we're repeating the steps. Afterwards, it goes into a sintering furnace. This is really just a batch process. It's a big oven. And what comes out is dense tool steel, like I have here on my desk. So hopefully that process makes sense. But what really matters is the result here. We say we get you essentially a Synchro EDM finish, Charmy 2062, sort of a matte finish on the part. Of course, if you want to polish it, you can do that afterwards. Tolerances of about 1 thou per inch. So on a 3-inch part, you'd be about plus or minus 3 thou. Really, really fine, sharp features thanks to those cutting tools. We often are told that we're essentially EDM sharp, so equivalent of what you would get with a Synchro EDM process. Stable, durable, trusted tool steels, H13 and 420 stainless. Very, very easy to use. And of course, what we're talking about today, conformal cooling, the ability to incorporate these complex cooling channels to reduce cycle times and improve efficiencies. Just have a couple really brief examples here. It's always great to have some fancy printing technology, and a lot of people have that. But what does it actually mean? It means our customers are saving time, they're saving money, massive lead time savings, reductions in the number of toolmaker hours involved, cost savings, some great cycle time improvements by incorporating conformal cooling. Just a quick durability example here on the right of inserts that have run millions of cycles. I think this one's going over 3.4 million today, thanks to those durable tool steels, H13 and 420 stainless. So what did this mean for our CITO application? This is just one little insert that you can see here. It's actually a really nice insert. Again, I'm not sure how well it's coming across on the camera here, but while it doesn't look too impressive on the outside, maybe what is great is that it has that really complex conformal cooling channel on the inside, which is really what we were after here. This is going to print in about 40 hours, so about a day and a half. It's going to go into that oven for about a day and a half, and then for about a fully burdened cost of about $800 to print just one of these. One thing I did want to include, of course, is that's a fully unattended process. So, this is what's coming out of the process. Maybe you give this to your toolmaker to do a little bit of finishing, grinding, or tapping of water lines or something like that. But we do actually get some great economies of scale because we can combine many of the steps. So I just wanted to include an example of that as well, where if you were to print 8 of these at once, instead of just 1.5 days for one, you could get 8 of these in 5 days. That sintering step, of course, is a batch process. So we can put all 8 in there at once for the day and a half. So in about a week, we're able to produce, 8 of these inserts for a much lower cost, of course, because we're getting some great economies of scale. Next steps here, the inserts are printed. It has that great, this wouldn't be that impressive to look at if you didn't know it had that awesome channel on the inside. We're going to send it over to Max and team. We'll do a little bit of grinding just to make sure it's perfectly fitting into the mold base. We'll finish off those ejector pins. Then we'll go ahead and do some testing, measure some cycle times, and of course, incorporate this with some of the stuff that Max is about to share for the next step of this project. But thanks for including me. And with that, I'll turn it over to Max.
All right. Again, I'm just going to start with a little background. CITO started in 1965, tool and die shop, as well as a custom molder job shop. PulseCooling was born in the late 70s out of necessity of not being able to produce quality parts for our customers. It was just a constant struggle. Then in 1980, CITO introduced PulseCooling to the plastics industry as a proven technology to reduce cycle time and boost quality production. Our involvement in this project is that we had a tool for a customer that needed to be updated with new inserts. They were getting worn out just from years of production. This presented us with a great opportunity to evaluate our tool and our process to make sure we were getting the full potential out of our cycle, and as well as to compare conventional cooling versus pulse cooling to show the many cost-saving benefits. We met with SimForm for analysis, and they recommended a 3D printed insert to accommodate conformal cooling where the hotspot was recognized. As the proprietors of PulseCooling, we knew that the benefits of having a conformally cooled insert along with PulseCooling would produce more than optimal results. So to begin the study, we wanted to look at the to compare conventional cooling versus pulse cooling, so we had real-time results to present to SimForm. Most processors today can cool the conventional way. They hook up a TCU, set a temperature, monitor the part quality, and make adjustments from there. Although simple to set up, this way of process cooling is not efficient. There are many disadvantages that are associated with it. The two biggest issues that we see is you have a very narrow delta T window here, which results in a slow heat transfer. You're trying to remove heat from your process with warm water. Cooling with warm water just does not make sense. The second issue is there's no direct control of the heat exchange on the molding surface itself. Both of these together result in longer cycle times and unpredictable parts after ejection. All the control adjustments have to be made shift to shift, day to day, season to season, depending on ambient temperature, cooling water available, supply pressure changes, etc. You are the controller 24/7. This becomes very costly. You have a technician or a process engineer making retroactive adjustments based on the part quality, which ultimately results in scrap because of the inconsistent parameters from run to run. All of these issues are the reason that pulse cooling was born. Pulse cooling will compensate for all of the disadvantages associated with conventional cooling. The controller makes proactive adjustments to maintain mold surface temperature during the entire molding cycle. This results in excellent mold fill, efficient heat removal, cycle time savings, and consistent part quality. When we look at the anatomy of the pulse cooling cycle, when we start the injection, we get a good mold fill because there's no opposing cooling going on during that mold fill. The cooling does not turn on until the sensor set point is reached. Once that set point is reached, the valve opens and sends a calculated pulse of water until the sensor is satisfied. Since we're sending the coldest water possible from the cooling source directly from your chiller or tower or tap, with turbulent flow, this results in a wide delta T and efficient heat removal. Once the cooling is shut off, the water warms up, the plastic cools down, and your mold will seek thermal equilibrium from there. Once the pulse cooling cycle is optimized, then no matter what the temperature or season or any other variable that you'll have in your cycle, it will make those proactive adjustments to maintain that mold surface temperature profile to mold a consistent part 24/7. As you can see, the cycle time reduction comes from that wide delta T. That's where we're pulling all the energy out of our mold with that calculated pulse of cold water. The cycle time reduction from efficiently removing the heat by sending that cold water to where it needs to go offers us the largest potential for profit in our cycle. So how does it work? First off, we have a typical mold here on our left. We have our pulse cooling controller. This is where you set the temperature for different zones, type of cooling you prefer. We have up to 9 programs of cooling based on your part geometry or how you want to cool the part. We have just regular on-off cooling, timed cooling, machine sync, PID, just to name a few. This controller can be machine mounted. This is our DOS-based touchscreen controller. We also offer a Windows-based controller for more in-depth monitoring of your process. Next, we have our supply and return valve banks. These can also be machine mounted. So with both of these being machine mounted, you take up no floor space around your machine. The supply, as mentioned, comes directly from the cooling source, the chiller, tower, tap, to our robust series of valves. These valves are named for being a stackable modular valve with numerous types of supply and return options. The supply is the stack valve, which is a 24-volt diaphragm valve, 24-volt DC diaphragm valve that has a removable screen as well as a visual flow turbine to see the flow through your zones. The return is what's known as our stack flow units, and this is just a ball valve that also has an integrated screen inside of it. Next is our sensor junction boxes. These are just simple junction boxes that can be mounted to your mold or to your machine, so you don't have to run your sensors all the way back to the valve banks. These come up to five zones. And then lastly, we have our sensors. In this case, we have 3 sensors on the stationary side, 2 on the movable side to ensure that we have a consistent temperature profile across our molding surface. The image on the right just showing a typical pulse cooling cycle, showing the melt being introduced, the energy from that melt warms the molding surface, sensor responds to the temperature rise, that opens the cooling valve once the set point is reached. The cooling comes directly from the chiller or tower. You have full flow turbulent cooling until the sensor set point is satisfied. Cooling valve closes, your heat dissipates uniformly, part ejects, and you have complete repeatability 24/7. Our applications for pulse cooling include, but are not limited to, injection molding, injection blow molding, extrusion blow molding, or any other cyclic process that requires cooling or heating up to 300 degrees Fahrenheit. We have multiple sensor styles available based on the complexity of your tool. A simple drilled hole will accommodate our mold steel sensors you see here on the left. These sensors are used to get as close as possible to the molding surface for real-time feedback. If you do not want to modify your tool or simply don't have the room, we can utilize our sensors to be placed directly into the water line here. This is our internal wet sensor with a quick connect flow-through coupling. The sensor length here is determined on where you want the reading to take place. Obviously, closest to the molding surface will optimize your results. We've had guys put them in eye bolt holes, lift mount holes, and just because they are reading that real-time temperature of the mold steel, they still were able to optimize their cycle times. If you do not want to impede your flow line, your water line, we have an external sensor that is placed up here in the fitting itself. Because the sensor is not in the mold steel or near the molding surface itself, we use a pulse advance program to advance our cooling media, so we can set when we want the media to advance and for how long to stay on to get the cooling where it needs to be in that tool. So now that we understand the advantages of pulse cooling and how it works, what is the outcome? The bottom line is pulse cooling has direct control over mold surface temperature, quality monitoring and control during the process, consistently higher quality parts, consistently faster cycle times, higher production yield, fraction of operational and maintenance costs, reduced capital investment, all with an excellent ROI. And while we here at CITO and our numerous customers know the benefits of implementing pulse cooling, we were looking for a way for our future customers to predict and understand those benefits before the first chip even hits the ground. So that's the direction we are taking with our recent partnership with SimForm to predict the results and with Mantle to manufacture the vision. So as Chris presented earlier, this is the mold we are running the case study on. This is the current state of the mold was in when we compared the 2 cooling methods. We have a sensor on each half with the water lines coming in and out, as Chris explained earlier. The sensors are drilled at within an 1/8 inch of the molding surface on each respective half. This is so we have real-time feedback of what is happening on the mold surface itself. This is the part that we ran an analysis on. It is for a customer of ours in the agriculture industry. As I mentioned, the tool is just getting worn out, needed to be updated. We need to maintain absolute control of the mold temperature on this tool to protect the mating shutoffs. Being that we do not use conventional cooling in our molding process, we decided to run the process both ways to show real-time results. As Chris mentioned earlier, we're coming in with a 40-degree cooling supply and a 40 psi system pressure. We recommend a 40-degree delta T and 40-degree system or 40 psi system pressure to achieve optimum results. With that, we saw nearly 50% reduction in cooling time, which resulted in a cycle time reduction of nearly 40% when using pulse cooling compared to conventional thermalator cooling. This was all achieved while still maintaining final dimensions and part appearance. Moving forward, we are going to introduce the conformally cooled insert that Ethan at Mantle printed for us. This is just an example of how we're going to zone. You can see the insert in here. That is where we're going to run our cooling through. And then we are going to implement a third sensor, zone sensor, to monitor that molding surface that we saw was going to be the problem. So now that we have a preliminary design, our next step is to compare running the conformally cooled insert with and without pulse cooling to show the true output of these three technologies put together. And with that, I'll send it back to Chris to show us how we're going to predict the improvement with pulse cooling.
Perfect. Thanks so much. I think it's really exciting that we're seeing all this come together, marrying all the technologies, actually seeing the insert printed. You can hold it in our hand now, and it's going to be exciting to put it actually within the mold. So obviously with all these technologies together, there's an element of foresight that we need to bring into things so that we can actually predict the improvement with the addition of pulse cooling on this third circuit and make sure that we're establishing the set point correctly, and also the temperature of the water as well. So I'm only showing some preliminary results for now, but what we're able to do and simulate in SimForm is the warm-up period for the mold. So where the pulsing action of the pulse cooling system hasn't yet engaged, but once the temperature at the key sensor location hits that certain threshold, that's when the pulse cooling kicks in, and then we see the temperature drop back down. So now that we're able to simulate this, we can start to prove out not only the cycle time savings, or match the cycle time savings that was already shown with Max's original experiments and production runs, but also show the additional savings that we get with this printed insert. Like I said, we can optimize the set point and optimize the sensor location for that process. And here's a little, let's see if it's going to animate for me. Here's a little animation of actually the pulsing action happening within the mold. So you see it starts out warm, and then all of a sudden the cooling channels start to engage and cool down the rest of the mold and get heat removal away from the part. So this is actually simulating the pulse cooling action on one of the existing channels within the mold. The next step will be doing so for the conformally cooled channels. So we're really excited to get this going and test it out on the actual press. So just a brief conclusion. What we've shown today is that we can use generative design to produce recommendations for where channels need to go and design a conformal cooling insert. We showed we can use modern fabrication technologies to produce that insert with novel 3D printing. We've also showed closed loop control using pulse cooling to try and avoid overcycling and ultimately overall reduce the cycle time. And like I said, in terms of next steps, we're going to produce experimental results with and without conformal cooling insert printed by Mantle. With and without pulse cooling, we're going to do some experimental correlation, and then we're going to use SimForm to help select that set point, the sensor location, and the water temperature. And we look forward to working on the next steps of this project. So that's pretty much it. I want to thank everyone for their attention for this joint webinar. I think we all really enjoyed putting this content together and sharing it with you today. If there are any questions, you have all of our contact information here on the screen. If you want to book a free meeting with us here at Maya to help go through your next mold design, you can scan the QR code, and Max is offering free consultation for new customers, and Ethan is available to talk about how their 3D printing technology can help with your next molding project. So thanks again for all of your attention, and I think we have a little bit of time for questions. So turn it back to Tim.
Yes, thank you. Let's take some questions from the chat window. First question, is there any limitation in the selection of steel for printing, or any kind of steel that can be printed to get the required inserts?
Yeah, so today we offer H13 tool steel and 420 stainless steel. Those are the two we offer today. It meets a wide percentage of the market, especially on the H13. Eventually we'll have more steels. Those are the two today. There's quite a bit of development work that goes into achieving the tolerances and the finish that we're doing with our process today. So those are the main two we have today, but in the future we'll add more. I'd be curious to know what specific steel you wanted. If you want to throw that in the chat, but those are the only two we have today, I should say.
Okay, next question. What inputs and criteria are used to generate the cooling channel recommendations in SimForm?
Right, so the main inputs that you need to provide for that generative algorithm are, first of all, the distance that the channels are allowed to be from the part surface. So how far away you can actually design the channels, basically the offset distance, a target diameter for your cooling channels, and an idea of the thermolator temperature, the water temperature, so that when we run the simulation afterwards, we're actually giving you more meaningful results given what is present within the production floor. And ultimately our objective, or the objective function for the optimization, is to try and get as uniform a temperature on the surface of the part as possible. There's like an indirect relationship between risk of warpage and temperature uniformity, again, as we all know. So that's the objective of the optimization.
Okay, next question. What is the difference between hybrid manufacturing method proposed and powder bed fusion technology?
Yeah, so powder bed fusion technology is using a powder instead of a paste as we are, and they're actually directly producing metal components by melting or sintering the metal powder with a laser and applying a lot of energy to that powder to do the sintering at that laser point. Our technology is quite different in that we're printing the metal powder as a paste. So the powder is actually completely loose in this stage, but it's bound in this binder to create the part. Then it goes into a sintering where we're doing all of the thermal processing at once instead of selectively doing it. That also means we can very uniformly heat and cool the part during that process. If you've ever used powder bed fusion, you know there's a lot of challenges with controlling that heat for warping and the thermals involved. If you're adding a lot of heat and cooling a part very, very quickly, it can lead to some stresses. It also leads to some rough surface finish on the outside of the part just from the powder used in general, where we're machining this every single step, so resulting in much, much better surface finish. Just to give myself some credibility, powder bed fusion is a lot faster, but they're faster to the part you produce. But what's going to come out is going to require a lot more finishing than our process.
Okay, next, can you describe the control law used in pulse cooling?
Yeah, the control law is fundamentally different from the traditional constant flow cooling. Rather than maintaining a steady state coolant flow, pulse cooling uses an on-off pulse flow strategy, dynamically controlled based on the real-time thermal feedback from the mold surface. A breakdown of how it works: you have the melt come in, then the input signal from the sensor gives the thermal feedback to the controller. We have a K-type thermocouple is what we use for our sensors. There's a set point temperature band, a high and low setting above your nominal set point. And then we use a pulse logic to turn on and off to send the cooling to the zone that it needs to be. It's a timed control. It automatically teaches itself. The controller teaches itself when it needs to cool and where the cooling needs to go. Just a quick summary. It's an on-off cooling from thermal feedback. The control variable is the mold surface temperature. The solenoid valve is the actuator. And the objective is to maintain surface temperature with the narrow band while minimizing your water usage.
Okay, next question to Ethan. How do you control the surface finish or surface roughness during the fabrication?
So the surface roughness is going to be the result of the machining steps that are happening. So it's going to be pretty consistent depending on the exact geometry. So you don't have the option to change that finish as much as we're trying to get it the best we possibly can with that machining step, which the limitation there is simply just the machining that's happening rather than, to get to a mirror finish, something like that, you would do a polishing step or a traditional step that would go beyond the finishing that's capable with machining.
Okay, next question. What is a typical runtime encountered with simulations in SimForm?
Obviously, it depends on the size of the mold, but usually, you're talking about less than 15 minutes to get a simulation. And that's a full transient simulation of the injection molding process, including that heat up period that you saw in the plot on the third to last slide there. I think I failed to mention in the presentation, but the way the software is built is that it actually runs on GPUs or graphical processing units like those that you have on your gaming laptops or your CAD workstations. These, of course, are available in cloud infrastructure. And as a result, we can run our simulations in highly parallelized fashion, and that's what we're able to produce results so quickly. So yeah, the whole point is to have simulations be convenient so that they become part of your design workflows and design process.
Okay, next question. How did you design the conformal cooling channels that ended up being printed?
Oh, that's a good question. So I think it's actually Ethan and I discussed it together. So initially, what you get from the optimization is those regions that you saw on the picture, but then also some what we're calling center lines. So center lines through those different regions that are being recommended. And then you can, in your CAD system, NX, SolidWorks, whatever, actually design like a spline through those points and then extrude a channel cross section through those points. That's the process that we used here. The additional step, and Ethan, you might need to or want to comment on that, is so the raw design was with a circular cross section, but for 3D printing, in order to be somewhat self-supporting, you need a teardrop shape. So that can also be accomplished within the CAD software. We're also thinking of providing tools within the SimForm platform directly to do some rough channel layouts. so that you can evaluate the conformal cooling design and then refine it and make it more precise within your CAD system. But I don't know if you wanted to add anything to that, Ethan.
Yeah, just to add that today we don't have a support material and we're not printing at a powder base like some other methods. So
Right.
we can't do too big of overhangs. So depending on the size of the channel, we'll do a sort of a teardrop shape or a diamond shape that is a self-supporting shape to ensure that that the channel has nice definition.
Okay, it looks like those were our questions. Thank you for an enlightening presentation. Do you have any final comments?
No, I just wanted to, thank SPE for helping us organize this. Thanks to Ethan and Max for participating. Like I said, I think we're excited to take the next steps and actually put the insert in the mold and instrument it up and actually start producing results and match those to the simulation. So I think it's really exciting that we're able to show the benefits of all of these three technologies combined together to ultimately, produce better parts and get better throughput in your production processes. So thanks again to everyone, and see you at the next webinar.
Very good. You'll receive an email with a link to the presentation and recording. Please be sure to check out our upcoming events and have a great day, everyone.
Thanks, everyone.
Thanks.
Thanks, everyone. Bye-bye.